would like to introduce a proof of concept project I did for the robotics recently in the next 5 minutes. And a first introduction. And in this very small proof of concept, I learned how does the business start the robotic project. And basically, business purchased the robots hardware. The hardware also associated with the software in the GitHub. That is typically, and how to make these work for business. And how does a professional learn robotic engineering? I learned foundations and models and pipelines from this proof of concept. And my background is not from the robotics, and I'm from enterprise AI solutions, and I have 8 years IoT and IIoT and edge experience, which is highly relevant to the robotics. And in these slides also have some robot basics, very high level. The robots just have the brain and have the body, and the brain have the different collection of the models. For example, the leg and arm is different. Like leg is mostly by the reinforcement learning, and it's called a PPO, and arm is called ACT, and it goes through the imitation learning because arm need to do something. And they also have the vision and the language models and VRM, SRM. And recently, the trend is integrate everything together, become a large foundation model. It's called a World Foundation Model. It's combine the vision, language, and action. But in this demo, we go to the very basics, go through the ACT model, imitation learning. The body from the hardware perspective, including legs and wheels and arms and hands, again, from I already introduced, they are governed by the different models. And the second thing I want to learn, I really learned is the pipeline, the coding. The pipeline is very standard and all in the software first, starting from the data preparation and collect the raw data and also convert it to the standard format. It's called a Lerobot, and start the training process. If we get the data prepared after the training process, and then we can evaluate the model and to see if it's ready. If it's ready, we can deploy that model to the physics robot. Of course, I do not excise the like sim to real part, but I deployed that to the evaluation and same thing. And what tools we use? There are two tools which I think that's very important to understand. So the one is the well-known NVIDIA Isaac Sim. That is the must-have for the production. And but there is a cost because it's need GPU. And I saw the price is the NVIDIA GDX Spark is $4,000 currently. But the good news is the Mojoko, that is the POC and the lightweighted, and also the prototyping tool that is free. And any computer can be okay. The trade-off is the simulation. It's not real. It's like the video game like 30 years ago. Not the real video game, but it's good enough to practice the how to exercise the robot apply to the business use case. Now, this is the workspace of the chosen pick and place. The chosen is the American's robot OEM, and they have some code already published in the GitHub. I just use that, but I have to modify that, simplify that, and because my use case is extremely simple. And the first step is to get the expert system, and it's the original code of the chosen code, and then I can show you that expert demo. I just modify the existing code to make the simplify the use case using this arm and to pick up the cube and then place into the bucket, as you can see. So this is the chosen arm, and pick up the red cubic and push that. Yeah, we need to imagine this is the real video and we take from the real life. But everything right now is simulation. Sometimes it's confuse me. So it's a real. But the problem is we need to take many pictures in the videos with the different positions, let's say 50. That will cost a lot of time. That is the major things for the cost issues for apply to the training for the business case. The good news is Mojoko can use the random number to generate simulations, and the NVIDIA Ice Sim can generate more real, depending on not only the position of the cube, correlation of the bucket, but also based on the light, based on the texture, based on the fractions, and also can do the job. So, so the first step now in conclusion is we need to prepare the raw data. We have the raw data, but I make it empty because this is like 26 gigabytes. When it's generated, it's too big. I just keep it small. I generate and then transform to the robot, and you get this data, and then start the training. And how do they start the training pipeline? And we will say, hey, this is the normal case. Say, hey, I purchased it, I installed it. It's governed by the random number. So the arm looked like crazy because all it's simulated by the random number. And then when we start the training, maybe you started from the first IP code and how the arm looked like. The arm is looked very stable, and then because they don't know, they have not learned yet how to pick up the cube and drop to the bucket. After the trend, it's I set up about 30,000 steps, and with the batch size is 8, and then to training this about 2.5 hours, maybe 3 and 4 hours. After the training, I get these results. I think it's good. It didn't totally learn it, but it's try to learning. See, it's just like a little bit problem. They cannot pick up the rate of cubic, but they do want to try to capture that and moving that. The problem is it's not training to the enough steps, and it's suggested to increase to the 60,000 or increase to the 90,000 steps, but I have not do that. For me, for the learning purpose, that's enough because my goal is to learning the pipeline. So now we already understand the fully pipeline, get the expert system and generate synthetic data with the different situations of the correct system. And then we using this training set to training that the arm we have and the digital arm we have. And after we training that successfully, we get satisfied, we can deploy it to the physics. So that's the whole idea. Now go back to the conclusion is how to deploy the robotics solutions. We get hardware we purchased from the OEM, and we get software part also. We get the kind of the digital twin, right? And then we put this digital twin of the robot into the semantic environment, like a simulated environment which we want to deploy to, and then we can use the Mojoko and using the Ice Sim to train that. After train successfully, go through the pipeline, and then we can deploy to the physics robot. It automatically can work, right? And also, my experience on this is it's really easy get job. So most work is go through the model training. That's the key we want to understand, and this kind of training is has no difference from the classic data science training we have experienced, and less needed from the software programming. We really don't need to fine grain it to control the leg or arms using the computer codes anymore, because it's kind of controlled by the foundation model, and also vibe coding everywhere. It can dramatically increase the efficiency of the learning. And I think that's all I want to share. And thank you very much.